Swayam Prabha. Digital India. Educated India.
So today I want to talk about polymers, microstructure and morphology. So basically the question that we would like to ask is, when we look at polymer, what do we know about polymers? Polymers are nothing but long chain molecules that are formed by combining smaller units together. And so we looked at various chemical aspects. What are all the type of atoms and elements that go into the making of a polymer, and then some properties like linear polymer, branched polymer, cross-linked polymer, thermosetting polymer, thermoplastic polymer. So various kind of characterizations. So now we are going a little bit further in. We ask the question like, so if you think about any plastic products, right? What is the form that we use them by? In what form are they? Do we use them? Solid, right? Solid, films, fibers, typically a solid like forms, right? And there are other situations where we want them polymer in a solutions too, okay? But broadly as a plastic, we have products that are in some sort of a solid form. So we know that individual polymer chains are long, flexible. There is a lot of rotation and bending and all that. On the other hand, when we actually use those material, we use them in a solid form. So the question is like, what is the nature of this molecular arrangement in a solid? Okay, we are asking this question because we are very much used to metals, okay, and we know metals, we use them as a solid, and we know in metal atoms are packed in a very regular lattice. They have a crystal unit. There is a lattice parameter. There is this strong ionic bonding that keep the atom together. So we know a lot about metals and metal properties. Okay, individual atoms coming together and forming a atoms coming and sitting in a regular positions. Okay, there is a symmetry involved. Now we ask the same question when we go to polymer, which are also solid, but we know that they are not like metallic atoms. They are not individual atoms. They are actually long chain molecules. So how are these molecules packed inside a solid object? Okay, and the second question is it really relevant to know about those internal structures of this polymer chain? And is there any effect of this packing of these molecules in a solid to the properties of this material itself? Okay, so those are the questions that we would like to ask, and today's discussion is to address these two questions, right? Now, if you think about a simple polymer like polyethylene, okay, and then if you try to make a small film, okay, maybe take polyethylene, put it in some solvent, you get a polymer solution, and then you cast into a film. And then if you look at the film structure in using some microscopic techniques like, so this one is the transmission micron electroscope, scopic image, you see that the structure is indicating some sort of crystalline structure. Okay, so you would see this kind of structure when you try to make a small film of a metal film. Okay, metals also crystallize, they form crystals. So even polymers also can actually form crystals. Okay, so that's new information. Even though we say polymers are long chain molecules, flexible and able to twist and bend, but when you try to bring them into a solid state, you can actually pack the molecules in some crystal forms. Okay, so that means we are talking about crystallization of a polymer molecule, right? So we can actually do microscopy, X-ray diffractions to see what is the polymer morphology, right? And we also say something like crystallinity, so how much crystal, what extent of the molecules are in crystalline form. Okay, unlike metals, which all of them actually form one big crystal, single crystal or maybe a polycrystalline crystal, but polymers can also form many such crystals, and then there can be also amorphous polymer between those crystals also. Okay, so it is not possible to have 100% of the polymer crystal. Some extent of them can be a crystal, the remaining can be a unorganized or uncrystallized amorphous regions, right? So even though that from the properties point of view, metal like crystals are very different, metallic crystals, we mean they are very strong, brittle, and it takes a lot of high temperature to melt them. Polymer crystals can be a little bit less stronger, less brittle, but they have similar kind of an atomic arrangement in metals. Okay, so there is a good analogy between metallic crystals and polymeric crystal. So now if you ask, okay, what controls the crystallinity of the polymer? Two things. One is the chemical nature of the polymer is important. Okay, what is there in the backbone, what is there in the side group, do they accommodate nice packing or not? Okay, so chemistry is important, and apart from chemistry, how you process them, how do you convert a polymeric solution into a solid polymer? Okay, that also matters, whether you are going to do drying or whether you are going to do extrusion or whether you are going to draw into a fiber. Depending upon the processing conditions, the crystal nature can be controlled, right? So here is a kind of a qualitative comparison between polymer that are crystalline and polymer that are not crystalline. So those non-crystalline polymer, we call them as an amorphous or a glass-like, where there is no very well structured polymer arrangement. Okay, the polymer chains are randomly grouped, right? Whereas in the semi-crystalline, some part of the polymer is crystalline, the remaining can be amorphous. Okay, no polymer can be 100% crystal like metals. Okay, there is some extent, 70%, 80% of them can be crystal, the remainings are amorphous. So if you compare semi-crystalline polymer such as polyethylene versus amorphous polymer such as, let's say, polystyrene or so, you can see that there is a good difference between the two. Okay, when you have a semi-crystalline polymer, they usually have high strength, that means they can actually support a lot of load, and they are quite stiff, that means rigid, and they usually have high density, they can be resistant to solvents, chemical solvents, and usually they are opaque, that means non-transparent, and so they can be resistant to fatigue, they can actually operate at high temperature because of the crystalline nature, and it's kind of harder to control extrusion and high energy to process. So these are all characteristic of a semi-crystalline polymer. Okay, same polymer, if you make them into an amorphous, as I said, the crystal nature can be controlled not only by the chemistry but also by the processing conditions. You can process the polymer such a way that you actually avoid crystal formation, then you are making an amorphous polymer. So when you make the same polymer into amorphous, usually they will have high toughness, that means they can dissipate energy, okay, by impact, and they can have ductility, that means it's easy to deform them and shape them, and usually they are characteristic of low density because it's not crystalline, it's amorphous, so the packing is not very efficient, so density can be low, and so they could have lower mold shrinkage. What it means is when you mold a polymer into a particular form and upon drying there will be some shrinkage effect. Okay, so this shrinkage effect is minimal if you have a amorphous, and then it can be transparent, it can have less residual stress. So these are other operating conditions. I mean, when you try to make polymer into different mold, there are several issues: shrinkage, moldability, and other things. So you can see a lot of difference between whether the polymer is crystalline or amorphous. So what we are trying to say is that even though we know about polymer, its chemistry, its chain-like properties, when you try to convert them into a solid, you have a situation that you can make them into a semi-crystalline or you can make them into amorphous. Depending upon how they form, the property can be very different. Okay, so that's very important. Now, so I have just wanted to kind of give some important inputs about what we mean by crystalline homopolymer or crystalline polymer. What are the true natures? Okay, so when we actually take any material, when we try to solidify, you solidify from a melt or you solidify from a solution. You do this for metal, you can also do this for polymers too. Okay, so this is called a phase transition. We are going from one phase to the other phase. So if you consider metal, in metals, crystals form throughout. Okay, there is the nucleation can happen in multiple places, and all these crystals can grow. You get what is called a polycrystalline material. Between those crystals, you have something called grain boundaries. Okay, so that's what the nature of a metallic crystal. When I say metallic crystal, I am talking about, let's say, nickel, iron, copper, those kind of metals. Whereas when you think about polymer, in polymer crystals do not form throughout, it forms somewhere and it slowly tries to grow outward, okay. And that is because these polymers are made up of long chain molecule, so they are not easy to diffuse from one place to other place. So the nucleation and growth are mostly local, and that is why we say them as a semi-crystalline, because they are not completely crystalline. And there will be some part which are not crystalline and they are going to be amorphous, okay. And these polymer crystallites, we also call them as spherulite. I come back to this spherulite little later. And it is true that not all polymers can form crystals. Some are even if you change the processing condition, it is not possible that you can make crystals of all polymers, okay. There are only some kind of polymer that you can make crystal, okay. And typically if you ask which polymer will form crystals, which don't, you are basically asking some characters. Those characteristics are that you should have a very regular arrangement of side groups, okay, so that they can come together and pack nicely, okay. If you have side group which are more bulkier and irregularly placed, you will not be able to pack them close. So that means you will not be able to crystallize them, okay. And another factor is the cooling time. So when you try to cool a melt, from a melt to solid, when you cool, there is a rate at which you are cooling this, the temperature per unit time. That cooling rate also matters. If you cool very rapidly, you don't have enough time for the chain to rearrange, so you will not be able to make good crystals. But if you do it very slowly, maybe you give enough time for the chains to rearrange, and you can probably make a high fraction of crystalline polymers, okay. So chemistry is important, processing conditioning is important, and then how do you cool the solution or the melt is also important, okay. So these are some important points about how we control crystalline polymers. Like any metals or any crystalline metals, we think about unit cell, right. So unit cell is a repeating unit in a crystal. So if you pack the unit cells on 3 dimensions repeatedly, you basically build the crystal, right. Now you can ask the same kind of question for polymer crystals too. For a polymer crystal also there is a unit cell, okay, and it can be repeated throughout the space to get a crystalline polymer. So what I show here is a polyethylene linear polyethylene chain. Here we show 3 chains. You see there is a parallelepiped shown by a dotted line. This chain goes through the center. These chains go through the front face. There is going to be 2 more chains going to the back side of the face, which is not shown here. So in this unit cell, there are basically 5 chains that are packed, okay. And here you can actually draw the unit cell shown by this parallelepiped. So if you look from the top view, you will see this middle chain from the top view, this one. These 2 chains are these 2, and the 2 chains that are not shown on the back side are these 2. So that means in a kind of a square lattice or a rectangular lattice, you have 4 chains occupying the corner, 1 at the center, okay. So that is 1 unit cell, okay. Now this polymer actually goes beyond this. That means this will form unit cell of the this will form part of the unit cell subsequently also, okay. Whereas in atomic crystals, you will see that individual atoms sit in these lattice positions, okay. But in polymer, since it is a chain like molecule, this will go further to other unit cells also. So here it is shown into a kind of a cartoon form. This is a CH2 group here, there is another CH2 group here, and so on, so, okay. So there are about and you can also see that cell dimensions also given. The distance between these 2 is about 7.4 angstrom. This is obtained from the semi-crystalline polyethylene solid, okay. So just like how we talk about unit cell in a metallic inorganic metals, the same way we can talk about unit cells for polymer crystals too, right. And so if you ask how these polymers are able to actually form this kind of crystalline structure, so these are the cartoon that kind of depicts this. So you see this is a polymer that does not have any particular structure, Okay. So, this is called an amorphous polymeric material, okay, where the chains do not have necessarily any sort of arrangement or any orientation. Okay. So, amorphous polymer would have this kind of a randomly placed chains in the material. Okay. In an ideal crystal polymer, what you would see is that the polymer actually forms into a nice regularly repeating pattern through some sort of secondary interaction between the chains. So, you see, by arranging in this way, the chain interaction can actually happen and keep them in place. So, there is some sort of an orientational order, right. So, this would be expected for an ideal crystalline polymer, but no polymer is ideally crystalline. What you generally have is this kind of a polymer where you see that there is, at an average, there is some order, but there is also a lot of defects. There are chains that are making extra loop here, right, and you see that sometimes this one actually not participating further, another chain is taking part in the repeating units. Okay. So, this kind of the looping structure of the chain over and above is very typical of a polymer crystal. What is shown here is actually shown here into a 3-dimensional structure. So, it basically form a very thin plate like structure which is called a lamellae. Okay. So, whenever a polymer crystallizes, it crystallizes as a thin plate, and this thickness of this I will show later can be of the order of 10 nanometer or 100 nanometer. Okay. So, now this one can be now stacked further. So, you see this is one lamellae, this is another lamellae, between them you have some amorphous polymer. Okay. So, polymer basically pack here, and extra polymer can go and then become a little bit irregular, and then it can take part this kind of a crystalline arrangement in the subsequent lamellae. Okay. So, typically a crystalline polymer is basically a stack of lamellae. Between those lamellae you will have this amorphous regions. Okay. We call something called this tie points to refer to the amorphous region between the crystalline material. Okay. These amorphous polymer is the one that actually holds these crystals in place. If you chop off these tie points, then the lamellae can easily come off. Okay. This is also relevant from the biodegradability of the polymer too. Okay. So, if you want to degrade this kind of polymer, you have to target these amorphous regions through enzyme or through other chemical attack. If you are able to chop off these tie points, then you can actually break open this polymer. Okay. Then subsequently you will have this lamellae structure. You need a different strategy to degrade those lamellae structures, right. So, generally when we apply any stress or any sort of shear force, this tie points is one that going to conduct this stress propagation. If you have high number of tie points, you will make the polymer more rigid, more stiffer. Okay. So, this is how the microstructure of crystalline polymer is going to look like. On the chain level, you have this kind of arrangement, and this can actually grow in 3 dimensions, form a thin plate which we call as lamellae. Then multiple lamellae can grow on top of each other, and each of these lamellae is connected by this kind of amorphous regions. Okay. And these polymers we call them as a tie points, and those are the points that are going to keep this lamellae stacked together. So, now the another level of organization is that once these lamellae form, they can also self organize into much larger structures. Okay. And those structures we call them as spherulites. So, lamellae self organizing into large spherulites. So, what you see here, each one of the small thread here is actually lamellae. So, imagine very large number of lamellae coming together and forming these kind of big networks. You can actually see these structures in a cross polarized microscope. You will see this kind of a pattern which we call this Maltese cross pattern. Okay. And if you zoom in further, you will see this kind of crystal domains. So, this is one crystal forming a crystal domain, and there is another crystal. So, you can see many such polymer crystals crisscrossing each other. So, what are we talking about? Individual polymer chains. They form, the first structure they form is this lamellae, which is a thin structure, and as I said, this lamellae can be from 10 to 100 nanometer, depends on the polymer chain length and the nature of the chemistry of the polymer. Once this lamellae form, the lamellae itself can actually self-organize into larger structure, which we call them as a spherulite. The spherulite, what you see here, this entire structure here, we call them as a spherulite. Okay, and this can be of the order of 1 micron to 50s of micron. Okay, so if you zoom in further, if you zoom in here, you're going to see the previous this kind of lamellar structure. If you zoom in further, you will see something like this. Okay, and what you see, this wiggly line is basically, let's say in this case, a polyethylene. The backbone is shown as this line. So if you zoom further, you will see hydrogens arranged in a zigzag carbon-carbon atom. Okay. So what you're going to see is that we did an experiment with one of our student and my colleague. We took polyethylene polymer in water. Okay, polyethylene is a water-soluble polymer. It is basically like a it's like a polyethylene. It's called PUO, polyethylene oxide. Okay, so it's very similar to polyethylene, but there's an extra oxygen in the backbone. It's water-soluble. And what we do is we take a polymer solution, aqueous polymer solution, put a small spot, put a drop on a glass slide, and you let it in the ambient air, and water will evaporate. Okay, only the water evaporates, the polymer remains there. Okay, so soon or sometime the polymer will become very highly concentrated, then the polymer will start forming a deposit, and that deposit actually will lead to a crystallization of the polymer. So what I'm going to show is a time-lapse image or video of this drying process. What you see here, you see there is this background blue color and then there is a black color. Are you able to see? So this black color is the droplet that is drying. Okay, the backside blue is a substrate, glass substrate. You will see that this front is a drying front. When the water evaporates, this front will keep moving inward. Okay, because the water is shrinking, the water droplet is shrinking, and then you are leaving with only the polymer deposit. So let's see what we see here. So you see some sort of an undulation happening. That's the water front, and it's kind of moving slowly inward because it's evaporating. We are only seeing 1/4 of the droplet. I hope I'm playing the right movie. You see that the polymer starts crystallizing here. You see some bright spots. So what you see here is this first lamellae that I was talking about, right? The bright spots are those. Now it's actually rapidly drying, creating more such droplets, more such as lamellae. The frame is readjusted. Now you see the entire droplet. Yeah, you see that the last frame, if you see, that's the Maltese pattern I was talking about. If you look at this center, you see this. Maybe if you can see the back screen, that's better, I think, in terms of resolution. So you see that here also you can see. Yeah, you can see in those screens. So these are this lamellae, and then once they come close enough, you form this kind of big spherulites, and you see this kind of a interconnecting tiles kind of a structure, that is basically each crystal is actually moving in and creating this grain boundaries. Okay, so this is what I was referring to in the presentation. So this pattern that you see here, this pattern you get whenever you see this kind of merging of multiple spherulites. When this happen, you get this kind of structure. That's what I show in the video also. Okay, it's a very simple experiment. You can also try it if you like. Okay, any question at this point? So one more thing that is possible is that when these crystals grow, you can also try sometime you can actually direct the orientation of these crystals also. Okay, you do that by applying some sort of a strain in one direction. Okay, so that the crystals can actually grow in one particular direction, and you can see that here there is a strain that is applied in this direction. All these lamellae are actually packed towards this direction, so you can actually form more like a fiber like structure. This is called oriented crystallization. If you don't do this, the crystal will grow in all different directions. You are going to have a more like an isotropic orientation. But here you are actually targeting or focusing the crystal growth in one particular direction by applying an external strain, right? So what's the reason for doing that? Well, if you compare PET that is isotropically crystallized versus crystallized under some oriented direction, you can actually manipulate the Young modulus, the strength of this material. Okay, so you can see that the isotropic PET has about 2.5 gigapascal, whereas the oriented PET has about 14 kilopascal. The PET bottle that we have here is actually called biaxially oriented. It is oriented in two directions. So when you blow this bottle, there is a strain that is applied in two directions, one vertical, another one horizontal. So it's called biaxially oriented PET bottle. Okay, and that is actually related to higher strength than if you simply crystallize into in an unoriented or in an isotropic form. Okay, so a lot of information, right? Polymer by chemistry, changing one atom can change the property, right? That's what we saw, chemical dependence. Then within that, depending upon how you crystallize, how you process, and how the chains are oriented within this plastic can also change the property dramatically. Okay, so that's what I'm trying to show here, that you can actually apply stress strain to prevent formation of large spherulite and orient the growth of spherulite in one particular direction, and therefore control the mechanical strength of this material. So whatever I have shown before are crystallizable polymer. Which polymer can crystallize? What are the requirements? Which polymers will crystallize? Sorry? Polymers with side branches. You want to have some sort of a regular arrangement of the polymer, and then it should be able to have some sort of interactions too, change in interactions that can pack them together. Okay, regularity, symmetry, intermolecular forces, these are all required to have something crystallizable, right? Now there are so many other polymer which may lack this property, and we may end up into forming what is called amorphous polymer or glassy polymer. Okay, so amorphous polymer, glassy polymers are synonymous. And here the chains are randomly packed, like I said before. So this is an example of an amorphous polymer where there is no regular arrangement of the chains compared to crystalline ones. But even in this set of even in this amorphous polymer, this is amorphous from the chemical nature of the chemical nature of it. But then by processing also you can try to induce some local orientations. Okay, for example, here if you see commercial PVC is actually atactic. What is atactic? What is the atactic polymer? Side groups are randomly positioned in 3-dimensional. Okay, so there is no regular order. Such a atactic polymer will not crystallize easily. okay. But when you synthesize PVC, you cannot completely make only atactic. Some portion of the chain can become syndiotactic also. What is syndiotactic? Alternative arrangement of the side groups. They can form crystals, and isotactics are the best ones to form crystals because you have a very regular arrangement, uniform arrangement. Okay. Now, when you think about PVC, even though majority of the PVC is atactic, there could be a small fraction of PVC which could be syndiotactic. So, locally you can form small crystals, but those are very, very tiny compared to what we see in the linear polymers, which are crystalline polymers. Okay. So, that means you will see that this is a kind of low level of crystallinity that is seen. You can see that a very small local arrangement which is different from lamellae kind of structure I showed before. Okay. But here when you try to draw into films and fibers, you can also orient these chains into something like this. Okay. So, there is a small degree of crystallinity is also possible even for amorphous polymers due to this processing, drawing films, drawing fibers, etc. Now, whatever we have shown before are homopolymers. What's a homopolymer? What's a homopolymer? A polymer containing only one type of monomeric system, right? Now, what are copolymers? Two or more number of repeating units in the same chain. Okay. So, AB, ABC, ABCD, whatever, right? So, many times what happens is when you have a copolymer, they do not mix well in the solid state, they try to phase separate. Okay. So, the reason for that is entropic origin. Polymers want to be close to with themselves, not with others. Okay. So, when you try to take a copolymer solution, in solution you can have a very nicely homogeneous solution. When you try to dry them, you will see that the segment will try to phase separate. So, this phase separation can be a good thing or a bad thing also. Okay. It is a good thing in sometimes where you can have some sort of a reinforcement. It is a bad thing sometimes, then you have a difference in the properties on one side of the film versus the other side. Okay. So, but you have to be very careful whenever we deal with copolymers. It can be a 2-block polymer or it can be a tri-block copolymer, and there is always an inherent segregation and phase separation. Even in well mixed blends, you will see that segregation can happen at a very, very small scale. So, sometimes this microscopic segregation is an advantage, and that is because if you compare here, there are two kinds of polymer, A and B. A will try to segregate into and form small domains. You can see this is another domain of A, this is another domain of A. These domains are now embedded into a matrix of B. Okay. Now, when you have things like this, it is actually advantageous because these segregated domains can be rigid, can be glassy, whereas the background one can be more rubbery, more flexible. So, you are basically having a reinforcement for polymer A in this case. If you do not have this, segregation, if you have only polymer B, it is going to make a very rubbery or flexible plastic. By having this copolymer AB, these domains will give reinforcement to the background polymer. So, it is possible to change the mechanical properties by having this micro segregation. Here is another picture. This is actually a TEM picture. This is made up of tri-block polymer. First you have styrene, then you have butadiene, then you have styrene again. So, this butadiene is a rubber, styrene is a amorphous polymer, polystyrene is an amorphous polymer, it forms a glassy network. Okay. So, what you see here, these domains that you see, these are all polystyrene. Between those polystyrene you have rubber, okay, and you can make what is called this styrene butadiene rubber, which is very reinforced strong rubber. Okay. And we get this kind of microstructure by combining multiple monomers into a copolymer. Okay. So, microstructure of block of polymer is a whole lot of different area. Now, by changing the length of this block versus this block, you can change the morphology here. If you change the morphology, the mechanical property of this will change. Okay. So, there is a lot of things going on to change the morphology of the microstructure therefore and manipulate the mechanical property, to some extent electrical property and other properties too, right. So I have been telling about a crystalline polymer, semi-crystalline polymer, and is there a way we can actually quantify them? Can we say this polymer has a particular percentage of crystallinity, right? So there is a way we can actually measure them. To measure this, we need certain quantities. We need the density of complete crystalline polymer. We also need the density of amorphous sample. Okay, let's say if I have polyethylene sample and I want to know what is the degree of crystallinity of this material. Okay, to calculate that I need two information. One is what is the, suppose if I make this polyethylene into completely crystalline material, what would be its density, and I also make the same polymer completely amorphous, what would be its density. These are the things that we can measure. Okay, for example, the crystalline polymer density is actually obtained through X-ray diffraction unit cell. Remember I was talking about a unit cell of polyethylene crystal before. So that's a completely crystalline material. By looking at the unit cell dimension, you know how many atoms are there in that unit cell. You can find what is the density of that unit cell. Okay, so the density of completely crystalline polymer can be obtained from X-ray diffraction unit cell information. Whereas the amorphous polymer density can be obtained by measuring specific volume versus temperature. You take the sample, right, and then you heat it. When you heat it, at some point of time the crystal will melt, it will become very amorphous material. Okay, so you see that the heating curve, I think this is polyethylene. So you start from some temperature and you are heating and you are measuring the specific volume. Specific volume is nothing but inverse of density. So the specific volume increases, and then this is where somewhere there is a melting point, and then after that it becomes a liquid. So you will get these points from here. These are all specific volumes measured at temperature above the melting temperature. So what you do, you actually draw an extrapolation, you do an extrapolated line, you draw a straight line all the way here, and if this is my measured temperature, this is a temperature at which I want to calculate the crystallinity, you extend this line and get the specific volume of the amorphous polymer. If you get the specific volume of amorphous polymer, the inverse of this would be the density, right? Do you understand? So what I am trying to say is that you try to heat the polymer and melt it, and then look at specific volume versus temperature in the melted state. Okay, so here the polymer is completely amorphous, completely melted, and then you fit a linear line and extrapolate all the way to the temperature of your interest, because you want to measure the crystallinity of a given sample at a given temperature. So to the given temperature you extrapolate as a linear line. So you got both information. The crystalline density comes from XRD, and take the inverse of that, that will be your specific volume. This is coming from extrapolated value. Once you have these two extreme values, okay, specific volume or density of completely crystalline polymer and completely amorphous polymer, then you can define percentage crystallinity for a sample of given specific volume using this formula. Okay, this basically tells you the difference between amorphous and your sample divided by the amorphous to the crystalline difference. So here is an example. So let's say for some polymer, let's polyethylene, Vc is given, Va is obtained from this kind of a plot, and then you have a sample whose density is given. Okay, so from this density you can get the specific volume by taking inverse, and then by substituting here, in this example it becomes like something like 59% or 60%. Okay, so this polymer has about 59% of crystal, the remaining would be amorphous. Another thing you will note here is up to 60 degrees Celsius here, this specific volume versus temperature is linear, and after that it becomes a little bit curved, and the polymer actually starts melting somewhere here, and complete melting happens somewhere here. So unlike metals where there is a single melting temperature, for polymer you could have a range of melting temperature. Would you expect that? Do you expect why? Why would polymeric material have a range of melting temperature, not a single unique temperature? What could be the reason? If you take metal, iron, there is a one single unique melting temperature, right? Give or take few degrees depending upon how you measure and purity. But polymer temperature, here you can see this polyethylene actually melts over a range of temperature all the way from 60 to 140. That's a broad range, wide range. Why would you expect it, or how would you explain this? It is not 100% crystalline. Okay, what else? But even if it's not 100% crystalline, even if 60% crystalline, but the temperature range is quite broad, no? 40 to 160 is quite a wide range of temperatures, no? What could it be? Orientation of molecules. Imagine, so now you have a picture of this crystalline polymer, right, in your mind. What is it? What is that crystalline nature of the polymer? What is the model that you have in your mind? So when you think about metallic crystal, I am thinking about an FCC lattice. I am thinking about atoms in those corners of the cube, on the faces, at the center. That's my model. For polymer, how is it? So remember, I was talking about lamellae getting stacked up and forming a spherulite, right? And so in a three-dimensional solid, you're going to have this hierarchical structure. There are chain, there are looping into forming this lamellae. Then between lamellae, there are amorphous regions. Okay, so you see the melting of a polymer is a very complex process of involving melting of spherulites, then melting of lamellae, then the chains will have to diffuse out. And the chains themselves need not be of all same size. You could have chains of broad size range also. You could have chain having 100 monomers. You can have chains having 200 monomers. Okay, there is no way you can actually create a polymer molecule all having same length. The polymerization reaction is going to give you a distribution of chain length. So all these factors will give you a very broad range of melting temperature. Hierarchical melting of the microstructure, variations in the chain length, all of them are going to affect the range of melting. So there is no way to talk about melting temperature as one single value for polymer. It is always a range. If you are lucky, you can have the range being small. That's the best case scenario. Otherwise, there is always going to be a range of temperatures. All right. Now, how do we measure this melting temperature? We do what is called this DSC, differential scanning calorimetry. It's very simple. You take your material, you slowly heat it, and then look at how much heat is absorbed or released. Okay. Now, as you know, when you want to melt something, you want to supply energy. The material will absorb energy so that they can break open the secondary bond and the chain can become more flexible. Okay. So typically what happens is you're looking at what is the heat absorption versus temperature. You start your material at 90 degree and slowly you heat the temperature, you apply, you heat the sample and look at how much heat is absorbing. So from here to here, it's just a sensible heat. Okay, the temperature is just acquiring heat, increasing the thermal motion, but still the structure is intact. Somewhere here, the chain starts untangling. Okay, the crystalline order is now broken. So melting starts happening. You see there is a peak here. This is where this is the temperature. Much of the crystals are melting. Okay, and after that you have some other processes. So usually you do this kind of differential scanning calorimetry or DSC called in short. You look at these kind of peaks. Okay, and the temperature of the biggest peak is usually referred as a melting temperature of this. Okay, even though there is going to be a range of temperatures. For practical reasons, we mention the temperature corresponding to the biggest peak as the melting temperature. Now, this melting temperature is not a unique, as I said before. It can depend a lot more. For example, the melt temperature can depend on the lamellar thickness. Lamellar thickness can change based on the molecular weight and other conditions, right? The highest peak in DSC we refer to as a melting temperature, and as I said, melting temperature range is due to the difference in the chain length, and sometimes we add plasticizer. What is a plasticizer? What's a plasticizer? Hmm? Is it additive or is it a filler? What is additive? What is filler? What is a filler? What is an additive? Sorry? Function. All of them have functions. No, I gave a very clear definition. Microscopically visible. Visually visible. Which one? Additive or filler? Filler is your definition is for filler. Okay. So now, when you add something, and that is something visually can see, microscopically or visually, we call them as a filler. Something that is not visually seen or detectable or adhesives. Now, is plasticizer additive or filler? Additive? All of you say additive? Anyone say filler? Okay, so it's an additive. So when we add a plasticizer to actually make flexibility of the polymer, it can also have effect on melting temperature. Okay, so polyethylene, its melting temperature is 120 degrees Celsius. You cannot say that. Okay, it depends on whether it has a plasticizer or not, and various other additives too. Okay, and then what we know empirically is that the presence of plasticizer will decrease melting temperature because it allows more flexibility, so chain can easily disentangle at lower heat. Melting temperature can also decrease with chain length. Shorter chains will have smaller melting temperature than the long chains. And compared to two polymers, stiffer and flexible, the stiffer will always have high temperature. That's intuitive. One example is, if you consider this polypropylene and compare with the polyethylene, what's the difference between polyethylene and polypropylene? One extra methyl group, right? You have CH2 in polyethylene. In polypropylene, one H is replaced with one methylene group. So that's one little bulky group. Okay, so that presence of one methyl group can actually increase its melting temperature by 27 degrees compared to PE. A small change in one pennant group or the branch group can change melting temperature quite a bit. Not few degrees, 27 degrees. All right. I think this is probably my last slide. Yeah, maybe last but last. Okay. We're running out of time, but I'll just take few more minutes. Another important concept in polymer physics or polymer material is something called glass transition. This is also another temperature that demarks its mechanical property from going from a brittle to rubbery. Okay, we say from glass to rubbery. So what happens is, when you think about melting of a semi-crystalline material, you are talking about a phase change. It goes from solid to a liquid. That is a visible. That's a visible change of a phase change. There is another transition called glass transition. That's a second order transition where there is no discernible phase change. Okay, so this glass transition is a temperature. Below that temperature, the polymer will be glassy. Okay, very brittle, hard. Above that, it will become rubbery, which means it's flexible and soft. Okay, and this is one of the important property for a polymer. And in metals, we also have something called TG that demarks the brittle to ductile transition. In a regular metal, atomic metals, we have this brittle to ductile transition at TG, but in a polymer, the glassy means brittle and rubbery means ductile. Okay, so I think I have a slide to show lot of different kind of polymer here: polypropylene, polyethylene, lot of them on the left. This letter here means crystalline or amorphous. Okay, the top first 6-7 polymers are crystalline, the next are amorphous. Then the third column is the melting temperature. This is a temperature where you melt the polymer from a solid to a liquid. And there are two numbers, one is given in centigrades, another one is given in Fahrenheit. So you can look at the first number, that is in Celsius. And the last column talks about glass transition. Okay. So if you look at this polypropylene, polyethylene, they have negative temperatures, minus in centigrade scale, the TG are negative. That means above minus 35, they will become rubbery. If you take them below 35, minus 35, then they become brittle. This information is very important in the context of how you use them, where you use them. Okay. In my lab, some of my students are looking at making micron sized particle of various plastics. So how do you make micron sized particle of any material? Chemical engineers, how do you make a powdery material? Ball millet, some sort of a size reduction, comminution, grinding, ball milling, any of those. But if you take your polymer and if you do it, and you will not be able to make powder. You have to go to a temperature where the material becomes brittle enough, then you can grind them. Only then you can make powder. So if I want to make a polypropylene microparticle by grinding, if you do it at room temperature, nothing will happen. Okay. But if you take a temperature below minus 35, then the polypropylene will become brittle. Then it's easy to grind them and make a small powder. So to make a microparticle or grinding application, you need to know what is this glass transition. Okay. Also in application also, you want to know about glass transition because you have made a polymer, it's going to be used in some application. It may be room temperature or different temperature. You want to know at that operating temperature or usable temperature whether the plastic that you have made is going to behave like rubbery, or is going to behave brittle. That's very important. Okay. If you put the polymer in a situation where it becomes brittle, but you're expecting a ductile like behavior, you're basically failing in your design. So for any polymer, when we try to use them, melting temperature is one temperature that will tell you whether it will remain in a solid or liquid. There is another temperature that will tell whether the material will be glassy or rubbery. Okay. One example is all of you use this stamp, right? Stamp. The stamp has an adhesive on the back side. Under normal condition, room temperature, it actually acts as a glass. Okay. So it won't stick. What do you do? How do you use your stamp? How do you use a stamp? How do you paste stamp? Heat it. Do you ever have you ever heated a stamp to stick it? What do you do? What's the simple thing we do to? Yes, you put a little bit of a coat of saliva, right? Or maybe a little water. So when you actually put a little bit of water or saliva, that's basically a plasticizer for that polymer. So by putting plasticizer, the TG of the polymer comes down. So instead of, let's say, 40 degree TG, it can come to room temperature TG. So the polymer will become more rubbery, become more sticky, and then you paste it. After some time, this water will evaporate, will leave out, right? Then the TG will go up again to 40 degrees Celsius, which is higher than the room temperature. So the polymer will become glassy after you stick them, right? So manipulating TG and by adding plasticizer or by adding something else, manipulating the TG temperature in relation to the usable temperature is a very important thing. Okay. So for polymer, TG, melting temperature are very important. Okay. This is my last slide. There is one more temperature. So what are the temperatures we're talking about? There is melting temperature, there is a glass transition temperature, and the third one is something called degradation temperature. This everybody understands. Degradation temperature is a temperature where the molecules basically break into pieces, okay, not usable anymore. They are basically degrade. Okay, any polymer, if you heat enough, they'll degrade, right? So now these three temperatures are important: melting, glass transition, and decomposition temperature. Okay. Now here I have given some classification. If you have a thermoset, what are thermosets? What are thermosets? I mean literally thermoset. It becomes harder by heating because there is a cross linking happening, okay, and this is thermosets are always amorphous, okay. So if you make a thermoset which is amorphous polymer, you see I'm actually adding more and more layers. Initially we were talking about thermoplastic thermoset, now we are bringing another qualifier about whether it is going to be glassy or crystalline or rubbery, all that, right. So all the thermosets are amorphous polymer, okay. Now when you have a thermoset, usually you'll use them over a temperature range between Tg and Td. Tg is the class transition temperature, Td is the degradation temperature. You will put your thermoset for application in the temperature range that will span from Tg to Td. Whereas if you have an amorphous or glassy polymer, which could be a thermoplastic, the thermoplastic that is made up of amorphous or glassy, you can actually mold them, you can form them, you can process them above Tg because it will be rubbery, it's easy to put into some shape, and then you can use them below Tg. If you use them below Tg, it can be more like like I was giving this example of stamp, right? Okay, so you can use them below Tg also is fine. Now we have a semi-crystalline polymer, thermoplastic. You can actually form them above melting temperature. When you try to extrude them or when you try to melt them, it becomes from solid to liquid, pour into a mold, okay, and you cool it, it will become the shape of this mold, and you can use them below Tm. So this is also very important. For a given polymer, you should know where the Tg is, where the melting temperature is, where the degradation temperature is. This will tell you how to make this polymer into molded form, at what temperature range, and at what temperature we should use them. Obviously your using temperature has to be below the forming temperature, the formulation temperature, okay. So those are important. Okay, I believe that's all. It's a lot of discussion. So